Hello friends, and welcome back to the class. Now, if you let's quickly recall the concepts we have learned about orbit transfer and theory of orbits. First of all, the eccentricity epsilon, we can write it as 1 minus 4 c square sine square alpha into 1 minus c square, where c is equal to v by ve, ve being the escape velocity. Now, again this escape velocity, right now we are discussing a projection from Earth's surface. So, that is why we have to calculate this, we have to use the ve equal to 11.2 kilometers per second, right. So, this is the escape velocity from the surface of the Earth, but we will be facing situations where the projection is not taking place on the surface of the Earth, but it is taking place at some certain height from the Earth. So, this ve has to be recalculated, that we have to keep in mind. And also we have found out the condition for elliptical orbit. We have seen that if the velocity v is less than ve, then we have an elliptical orbit. Now, inside that also there are two regimes. If the velocity stays between v less than ve by root 2, okay, then we have, actually it should be v less than equal to root 2, right. Then we have a closed orbit which is called a ballistic missile, whereas for velocities ranging between ve by root 2 and ve, we have a satellite which is orbiting around Earth, right. Now, we also found certain condition for this, and we have seen that condition for getting a satellite. So, we did that by keeping in mind this particular picture. So, this is our Earth with radius r0, and what we have seen is, if this is my launch position, the velocity of the launch is v with an angle alpha with the horizontal direction, then we have seen that it can go like this in a revolving orbit, or it can come back like this in a closed orbit. Okay. So, this one is ballistic missile and this one is a satellite, right. This we have seen. Now, also we have found out for ballistic missile there are certain parameters which can be calculated. We have seen that for ballistic missile the relation is r for any point on the orbit. We have defined this angle as phi 0, that is the angle of the perigee or apogee, sorry, and any other angle is measured this angle as phi. Okay. So, this is measured, the angular deviation is measured with respect to the position of launch. We measured the angle with respect to a horizontal line which is drawn at the position of launch. So, using this we have seen r can be given as r0 1 minus epsilon cos phi 0 divided by 1 minus epsilon cos phi minus phi 0. So, this is the equation we have got. Okay. So, and from this equation we have seen that the r equal to 0 for phi equal to either 0 or 2 phi 0. Phi equal to 0 is the initial condition. So, the phi equal to 2 phi 0 is the position where the ballistic missile comes back to the Earth's surface once again, and from there we have calculated the range r is equal to r0, 2 times r 0 phi 0. Okay. So, r, this r is the range and this r is the radius of the earth. So, these we have seen, and these are all for this particular velocity range when the velocity is below v e. Okay. So, now what happens is when we have velocity equal to or greater than c or greater than v e. So, that means we have a situation where c is greater than equal to 1, and of course, we understand that this will lead to unbound orbit. So far we have discussed only bound orbits, and also in this particular case when v e equal to root 2 and alpha equal to pi, we have circular orbit, that we have also discussed. The condition for circular orbit is achievable when v equal to v e by root 2 and alpha equal to pi by 2, right. So, this is what we have seen. Okay. Now, for unbound orbit, which is given by c greater than equal to 1 or v greater than equal to v e. So, there are two cases. First case is when v is equal to v e, we get c equal to 1, and from the expression of eccentricity, if we put c equal to 1 in this, we immediately see that the second term in this eccentricity expression, if we put c equal to 1, this term will vanish and we get epsilon equal to 1 for any alpha. So, then we get a parabolic orbit, and also we have discussed that in this case the total energy of the orbit will be equal to 0. What happens if we have v greater than v e, that means c greater than 1, we have epsilon greater than 1 for any alpha, and we have a hyperbolic orbit. Okay. So, these two cases can be described by this picture. Once again, this is our earth. Okay. So, this center of the earth is the force center. So, let us assume that this is the launching position. Okay. It makes an angle alpha with the horizontal. Okay. So, for c equal to 1 or v equal to v e, we will have a parabolic path. So, how does this parabola look like? Please remember, we first have to, so we have to draw a parabola with, so we can do it like this. We can draw a parabola where the with one of the this force center at one of the focus. So, if we draw a parabola something of like this, right. So, essentially this orbit will be something like this. Yeah. Okay. So, after initial launch with an angle alpha, it will go and eventually merge with this parabolic line. Similarly, a hyperbola will be, okay, I will draw it with red. Okay. So, if we have a velocity which is greater than v e with the same launching angle, let us say, then the projectile or the object with after launch, it will go like this and essentially merge into this hyperbolic orbit and move away from the force center. So, this is the case where c is greater than 1, and this is the case when c is equal to 1, this and this, fine. So, now also we have a special case where when L is equal to 0. Now, L, which is given by mv r 0 sin alpha, or we can replace this r with some arbitrary radius, arbitrary distance r. So, this can happen if v is equal to 0 or alpha is equal to 0. Okay. So, this or both. So, this is the situation which will give us if L is equal to 0. Now, if you recall, L is equal to r square theta dot, which will be equal to 0. So, which will give you theta equal to constant. So, this will give you an orbit on which theta does not change. And if we so one particular case could be, let us say if this is our earth and we drop an object from outer space with 0 initial velocity. So, that means this particular condition v equal to 0 satisfies. Okay. So, that means L will be equal to 0. Now, if we just release it from outer space, so it will be attracted towards the force center. So, essentially it will travel along the line with along the straight line which connects this point and the force center with a straight line where theta will be equal to constant. So, this is a case, this is a special case with which is a motion with L equal to 0. And from our school I mean +2 standard physics, we know that if we allow this object, if we dig a tunnel in our along the surface of the earth or along the length of the earth, and if we allow an object to move back and forth, the motion will be a simple harmonic motion, that we know. So, let us not go into the details of that. So, the last topic which I want to cover is transfer of orbit. Here I will not be employing any mathematics, because that is not terribly important here. First of all, we are not going into the deep, we are not covering it in depth, this particular topic. And secondly, the calculations which can be performed are also sometimes oversimplification. So, best thing is if we just keep everything simple. So, the situation is as follows. We have, let us say this is our planet, our earth, and one particular orbit is one particular satellite is moving in a near about circular orbit with a fixed radius r. Now, what is the velocity on a circular orbit? If you recall, if this radius is r, then we can write this relation that half mv square, which is equal to v minus v of r by 2. Okay. This is not very important to understand the nature of orbit transfer, but also I wanted to just discuss this briefly. This happens because you are in a circular orbit, the total energy is given by minus v r by 2, and this will give you a velocity v, which is equal to root v r, there is a minus sign, by m, and if we put values, it will be simply root over. So, we can, if we take v r to be equal to minus k by r, so it will be k by 2 r. Okay. So, it will be k by m r in this case, okay. Or what we can, or sorry, the capital R, or if we put k equal to g m m by k is equal to g m m, then velocity v will be equal to root g m by r. Okay. So, this is the velocity. Now, as we see that the velocity is inversely proportional to the radius. So, what if we want to go to a higher or lower orbit? Let us say if we want to move to a higher orbit with certain radius r1, how do we do that? Okay. There are of course many ways of doing it, but there is a very special type of orbit transfer, or very common type of, or there is a very common way of doing it. There are of course other ways, which is called Hohmann transfer. So, what happens in Hohmann transfer is at some point of this orbit a rocket is fired. Now, for a circular orbit, at any point on the orbit, if you fire a rocket, the additional velocity will work perpendicular to that particular direction. Okay. Now, firing a rocket means you are putting additional energy to the to this system. Now, if you recall from the equivalent energy picture, this is the equivalent energy picture or effective mass potential of inverse square force field. Circular orbit is here. Higher to that, so if this is this energy E0, this is the corresponding radius r of the circular orbit, right. Now, if we want to, if we put some additional energy into the system, then what happens? We can move it slightly higher. So, it will be an elliptical orbit with two radiuses r0 and r1. Now, in Hohmann transfer, what is done typically is the velocity of the rocket, velocity of this additional thrust is adjusted such that the ellipse is drawn something like in this manner. Okay. So, this is an ellipse. Sorry, this is not a very clear picture. Okay. So, this is the force center as we know. So, this is my perigee distance and this is my apogee distance. So, we see that the relation is 2a, which is here to here, is equal to r plus r1. This is r, this is r1, right. So, this is how this energy of this particular and from here we can always write the total energy of this elliptical orbit, and then from there we can calculate what is the velocity needed, what is the firing speed needed in order to move to this particular orbit. Now, what happens is from here we can come here once. So, once the rocket takes this elliptical path, comes to this particular position, there is a rocket which will fire in the opposite direction. So, that means, if this is the direction of the satellite, the rocket will fire in this direction, so that the velocity component in this direction. This is needed because once again we have to come to this, we have to go down to this particular energy level, but this time with another r. So, what happens is essentially when we are changing the velocity, we are adjusting the L square by 2m r square component. Okay. So, remember this L is a function, L is something which is in our hand, this we can control. So, by carefully adjusting the velocities, we can compute another L which will give rise to another effective potential, okay, with a slightly higher radius which will be given by r1. Okay. So, please remember that this effective potential what we draw is a strong function of L square or L square by 2m r square, right. So, if we want to, if we change the velocity of the satellite in question, or that is in our hand essentially. So, what we are doing is we are modifying this effective potential. So, essentially in an Hohmann transfer, what we need to do is we need to go from this particular potential to this particular potential. So, that we start with a circular orbit with radius r, which is a minimum of this potential, effective potential, and then at the end we go to this particular potential with a radius, minimal at r equal to r1. Okay. So, in brief, this is Hohmann transfer. Also, we can do some simple calculation for this single burn maneuver, that is the transfer between a circular orbit to elliptical orbit, but we are not going into the details of that. So, let us move on and try to solve some problems. So, we start with this new problem set where we have 5 problems. Now, out of that 5, we will see how much we can do in the class. I wish to cover all of it. So, the first problem is that if the gravitational force between two bodies has been inversely proportional to the fourth power of the distance, find out the escape velocity at the surface of the earth. Okay. So, it is a hypothetical situation. Now, if we start calculating it, first of all, what is the nature of force we have? So, F, okay, so I will just take this pen. So, F is equal to minus G m m by r to the power 4. So, typically it is r square, as we all know, and we are discussing an hypothetical case. So, it is G m m by r to the power 4. Now, if this is r to the power 4, there is always we can find out the potential function, which will be minus G m m by r cubed, and there is a factor of 3 coming, because these two are related by F is equal to minus dV dr, right. Okay. So, with this we can write the expression for escape velocity as half m v e square equal to minus v of r 0. Please remember, we are calculating, we are doing this calculation for earth's surface, right. Okay. Now, comparing this two, we get an expression for velocity, and we use this expression for v r, and the expression for velocity is 2 g m by 3 r 0 cubed, right. Now, we can try to put the values of gravitational constant, mass of earth, so on and so forth, or what we can do is we can simply modify this by writing 2 g m by 3 r 0 square into 1 by r 0. Now, if you recall, now I am just I am coming back to the actual scenario where F is equal to G m m by r square with a minus sign. Here the gravitational constant V G is given by root over G m by r 0 square, right, and we know that the value is 10 meters per second square, right. So, G m by r 0, assuming that the radius of earth remains constant even under this particular force, which is again it is an hypothetical situation. So, G m by r 0 square root, the whole thing is 10, right. Now, if this is 10, then we have 10 multiplied by 2 by 3 r 0 meter per second square. So, this will be our answer. Now, if you compute this, we have to put the values. So, it will be 10 divided by 2 into 3 into 6400 kilometers. So, we have 10 to the power 3. This will be in meters per second. We have taken, oh sorry, it will be second because it is escape velocity, I am sorry. We have taken r 0 as 6400 kilometer, which is the standard value for average radius of earth, which is once again not very accurate. It is actually 63797 something, but we can, for this calculation we can take 6400. So, if you put these numbers, you will get a value for escape velocity. I leave it to you. I want you to finish this yourself, right. Now, let us move to problem number 2. Okay. Problem number 2 says a particle moves in a circular orbit under the action of this force F r equal to minus k by r square, which is the standard inverse square force, attractive force, which is given. If k is suddenly reduced to half of its original value, show that the particle now moves along a parabola. So, it is a tricky problem. Think of it this way. What happens? What we need to show is that the the particle which is moving originally in a circular orbit. Now, during its motion at some point suddenly the force constant k, which is it will be replaced by k by 2. So, it reduces by half. Now, we have to show that this path will change into a parabola. Now, I can tell you that we do not need to do, I mean we do not need to show that, I mean we do not need to calculate the equation of the path. Instead, what we can do is we recall that for circular orbit v is equal to root over k by m r. Okay, so, we are doing problem number 2 here, v, that is for a circular orbit. Now, what happens in a circular orbit, or rather now this is the situation here. So, we have a circular orbit with radius r, and any point we have this velocity or speed, rather we should call it speed, because which is technically more correct. Right. Now, if k goes to k by 2, okay. Now, at this particular situation, when the force is given by so force when k goes to k by 2, the force was k by r square minus, now the force is k by 2 r square, right. Now, if we look at the escape velocity expression for these two cases, initially the escape velocity v e, which is given by root 2 k by m r for a distance r from the force center. Now, the escape velocity will be given, because k has been reduced to half, it will be given by k by m r, because we are substituting k equal to k by 2, right. So, now compare this. So, this is the escape velocity and this is the original velocity. So, what happens is the particle which moves in a circular orbit with this particular force law, with force constant, with this particular force law, as the force constant suddenly reduces to half, the instantaneous velocity which was at any point of the circular orbit, which was given by k by m r, now becomes the escape velocity of that particle. So, what happens is, now for escape velocity, when a particle moves with escape velocity in an inverse square force field, we know from our discussion earlier that the path will be a parabola, right. So, that is why let us say at this point where the force constant has been reduced from k to k half, it will immediately start travelling in a parabolic path. So, your path will look something like this. So, it will go, instead of going in the original path, it will start travelling in this path. Okay. So, this is how we prove it. So, it is not a very straightforward proof, as we can see, it is kind of an intuitive answer we had to provide, but it is a very tricky, I mean it is a very it is a beautiful question, because initially when you look at it, you might have thought that okay, you have to solve equations for circular orbit and you have to show that the equation changes into something like an elliptical orbit, that nothing is needed. All you need to show that the particle which was moving with certain velocity, when the force constant reduces to half, it becomes the escape velocity of the particle, and that is it. And when it moves with an escape velocity, you immediately know that it is moving in a parabolic orbit, hence proved. Okay. So, problem number 3 is period of moon around earth is 27 and 3 days, earth to moon distance is 3.84 into 10 to the power 5 kilometers. Okay. So, there are 3 parts to this problem. We will for this class we have maybe only 2 minutes left. So, we will focus only on the first problem. What is the calculate the average height of a geostationary orbit from Earth's surface. Now, this is an application of Kepler's law. Okay. Remember, in Kepler's law, for if this is your force center and we have one elliptical orbit and other elliptical orbit, okay. I mean, it does not necessarily be on the epicidal points need not be on the same plane, I just draw it like this. So, this is one elliptical orbit, then other elliptical orbit. Then if these are 2a for first orbit and let us say this is 2a of second orbit, then according to Kepler's laws, T1 by T2 square is equal to A1 by A2 cubed. Now, what is given here is the orbital length, the length of orbit and or rather A of the orbit for moon and the time period is given. So, Tm is given as 27.3 days. Am, which is the average distance of Earth to Moon, which is given as 384,000 kilometer. Okay. The geostationary orbit, we know that for geostationary orbit, it is an orbit which stays on Earth on a single position of Earth and evolves along with the Earth. So, for geostationary orbit, T satellite will be 1 day. So, if you are not familiar with the term geostationary, I would suggest that you kindly look it up. You must have heard of Indian INSAT satellite. INSAT satellite is a geostationary satellite, which during all the day, I mean every minute, every second after its launch, it is being placed on a single, I mean it is the relative position with respect to Earth of that particular orbit is, I mean a particular satellite is not changing. Okay. So, that is the definition of a geostationary orbit. So, geostationary orbit has a time revolution or time period of 1 day. So, INSAT is placed directly on India. So, there are each country has their own geostationary orbit which will be placed directly on that particular country, and it will evolve along with that. As the Earth moves, Earth rotates, it will also rotate along with the Earth. So, we have Ts equal to 1. So, we have to calculate As. Okay. So, when we put it into this equation, we get As equal to Ts by Tm whole to the power 2/3 into Am, which will be 1 by 27.3 whole to the power 2/3 into 384,000 kilometers, which will be 42.354 kilometer, approximately 6.6 R0. Assuming that R0 is equal to, R0 is the radius, okay, it is 6400 kilometers. So, we see that if this is R0, then 6 R0, which is somewhere here along above this height, a geostationary orbit must rotate. So, each of these orbits has a very specific name to it. We are not going into the details of it. There is a lower circular orbit, there is an upper circular orbit. Okay. So, but geostationary orbit is something that we are interested in, and we have seen that it is 6.6 R0. Okay. So, for now we have to stop here. We will continue once again. Thank you.